That's what we were all waiting to hear. Recording is in progress. So I'd like to welcome everybody to the NAL First Thursday program. Today is October 3rd, and as of yesterday, it was the official end of baseball season. I'm Lisa Spence, and I'm your host for today. Our speaker today is Mr. David Petri. If you really bribe him, he can tell you about what a horrible employee I was when I was working for him. So at this point, David is the System Integration and Test Manager for the VIPER program. And VIPER stands for Volatiles Investigating Polar Exploration Rover. So it's a lunar polar exploration rover. So prior to coming to JSC, David worked for McDonnell Douglas and then at Lockheed Martin for about 7 years. He started his career at JSC as a senior system engineer in 1989 and has filled a number of technical and leadership roles in virtually every program that we've had here at JSC. He served in the Safety and Mission Assurance Directorate a couple of times, once as the Flight Equipment Deputy Division Chief and later as Flight Equipment Division Chief. While in SNMA, easy for me to say, he was also the Guidance, Navigation, and Control Lab Manager, which included being the facility lead for X-38 GNNC flight software development, GNNC development and test deputy branch chief, and also served as a source board chair, which is why I now have figured out why he sent me off to a bunker. Following the Columbia accident, David.
That's what they told me.
Following the Columbia accident, David was the engineering co-lead for the accident fault tree team. And during the Constellation program, he was the SE&I program integration manager, the SE&I deputy manager, and the integrated test and verification manager. So David spent nearly 8 years as the Orion avionics and software test system manager. He was in the Ascent Abort 2 integration test and operations organization as a test operator and test conductor for AA2, the ejectable data recorder drop test conductor, and the day of launch console operator for the EDR, and as a backup flight vehicle operator. David has degrees in aeronautical and aerospace engineering, a bachelor's from Purdue University, and a master's from Stanford. He also holds a management certificate from Harvard Business School. And in his spare time, he has promised to serenade us with his guitar. And he also enjoys spending time with his family. David and his wife have been married for, get this, 40 years. They have 3 grown children who are, as he says, for the most part, no longer on the family payroll. So at this point in time, I'm going to invite David to come up, and I'm going to go ahead and share his presentation.
Thank you, Lisa.
It's hard to hear and all that stuff. I do owe a great gratitude to my wife. She's put up with a lot.
Go for it. Okay. You'll be in control of your slides. And just hit those buttons.
The arrow keys. Okay, very good. Yep. All right. As Lisa said, I'm the system integration and test lead for the VIPER project here at JSC. VIPER is again, a robotic rover, not human space flight. It's led out of the Science Mission Directorate at headquarters and is actually a project run out of the Ames Research Center. JSC's role in it is twofold. One is to do all the integrated design, and then I had the privilege of taking all the components and working with the team to put all the components together into an integrated spacecraft and then test that spacecraft. And I'm going to tell you all about that. Again, the main mission for VIPER is to prospect for water volatiles. You know, it's different constituents of hydrogen and oxygen. We know water exists on the moon, but we don't know the concentrations. And again, it's one of those fundamental questions that we're going to answer someday, which is, are the concentrations there enough to make it worthwhile to invest in all the equipment necessary to mine that water and turn it into all the useful products that we need it to be. again, it's a big swinger in the transportation architecture. If there's enough there and you put in the infrastructure, well, now you're not bringing water from the surface of the earth. If it's not in the right concentration, well, then you know you're gonna have to bring all that from earth and you build your transportation infrastructure that way. One of the really just fascinating things to me is that with that ground source or ground truth data, as we're exploring that area, they can then correlate that information to orbital imagery. And once you have that correlation, you now can get a basic water concentration map of the entire moon. So you get a first pass at, you know, where's all the water on the moon. It's just fascinating. The vehicle consists of several different science experiments. Obviously the Rover is the bus for it, but there's a 1 meter drill on board that allows us to dig into the surface and be able to pull up the pilings, measure the volatiles boiling off those pilings, and you can get a three-dimensional representation, at least down to 1 meter, of what the concentrations are. There are 3 different spectrometers on the vehicle. There's a mass spectrometer, there's a near infrared spectrometer, and there's a neutron spectrometer. So all 3 of those spectrometers are, again, measuring those volatiles and determining or giving information in order to make a determination of what the concentrations are. Another interesting thing is with the IMU, again, the primary purpose for the IMU is helping us with just roving navigation. You know, you're driving the vehicle off the IMU, but they can use the reverberations through the regolith as like a sounding. So when you put the drill into a percussive mode, you're pounding onto that surface, it sends out those waves, and then the IMU can detect those waves, and it can make some kind of more long distance concentrations of mass in the subsurface. There is, I guess there was some of that tried on one of the Mars rovers. Again, I don't think it had a drill, but they prototyped the concept for it. More importantly, they got the equations on it. So you run it through some algorithms and they can determine something from those soundings coming off the surface when you're pounding on the soil. The mission itself, we've designed the vehicle to last 100 Earth days. That gets us through about 3 days of day-night cycles on the surface. So we have to survive. We're always running away from the shadows, but there are periods of time where we actually will be in a shadowed region. We need to survive through that. So you'll see on there's a dark survivability requirement of about 50 hours where we're actually in shadow. Again, we're running off of batteries and solar panels. And so keeping track of that is really important. The other big driver is, let's see if I can. Trying to get rid of that. People can read the side, I guess not. All right. Anyway, the other big driver in the design of the vehicle is going into the permanently shadowed regions. Obviously, permanently shadowed regions, you'd think, well, the probability of water, ice, or water volatiles would be in those permanently shadowed regions because they're not sublimating off. And so we want to go in those areas so we can do about 10 hours of operations in those permanently shadowed crater regions. For driving, just how do we drive the vehicle? It's not Mario Kart. You know, it's not a remote control when you're driving it. It's much more like a remotely operated vehicle in the sense of you take pictures. Drivers on the ground are looking at those pictures and determine, hey, I want to avoid that rock. I want to avoid that crater. I want to go in this direction for about 3 meters. And they change the attitude of the vehicle and travel those 3 meters in that direction. And then they repeat the process. So it's a very controlled operation for driving the vehicle. And it's not like Mars either, because obviously Mars is even more difficult with the longer time delays. The vehicle weighs just under 1,000 pounds, 450 watts of power is about where we're at. COM is in the X-band region. We have a low gain antenna and a high gain phased array that we use. Vehicle's not too big. Think of like size of one of your larger golf carts, 5 by 5 by 8 foot tall. Top speed is not too fast. We can go up to that almost half a mile an hour on when you're just, we call it rails driving, if you just go. I'm not sure what I'm doing.
Yeah, it's real sensitive.
It sure is. I'll stop banging on the podium. But it's faster than most Rovers. The only thing that it's not faster than is the old lunar rover vehicle that the Apollo astronauts used. Where are we at in the project? That is a really quick overview of the vehicle, and you can ask me questions about that in any more details. Although, let me caveat, I am the integration and test guy. I have limited insight into the design or why design choices were made. I know how to put it together, but I don't necessarily know why it was that way. And I know even less about the science. I just know that we have 4 instruments on there, we're collecting all the data, and we're looking for volatiles. But I'll do my best. As with a lot of NASA projects, you know, this thing has been in the makings for a long time. There are people that have been working on the instruments for over 15 years. There have been a couple different instantiations of the project. The most recent one before VIPER was called Resource Prospector. It was done in the 2014 to 2016 timeframe, and I would say they did an advanced prototype of the vehicle at that time. Slightly different science complement on the vehicle, but it was a good basis for us to get started. They restarted the vehicle or the project under the VIPER name back in 2019, and we quickly went through requirements review, got through the preliminary design review, and in 2020, if you remember, we hit COVID, and that had a whole bunch of challenges with it. Luckily for me, I only had to stay working from home for only about 2 months, and we came back in because we had a facility to build and ultimately a vehicle to build. But a lot of people were working from home, which makes it really tough trying to do every meeting virtually. You just don't get enough bandwidth and communicating with people on this. The other even bigger problem though was the supply chain. Supply chain became a really bad issue, and it delayed a lot of our systems. Systems that you would think, I mean, you've all lived this, you never can expect them all, but the amount of problems that we had with our flight computer was difficult. The amount of problems that we had with our RF transceiver, just unbelievable. Part of it supply chain, part of it just in general. Part of it was starting the war in Ukraine and production lines in Europe switching over to doing, arms, military support hardware instead of doing NASA hardware. Some of it was just an erosion in talent. The talent in the industry, as far as I'm concerned, it's just spread very thin right now. It is really hard to find really good people that are going to take their time to go work on NASA projects. In a typical NASA project, yes, it was mostly off-the-shelf equipment, but again, we always had those little unique requirements that pop up, and the vendors buy into it, and then we pay for it, and then they couldn't meet the schedule. 2021, we had the critical design review, system integration review, which was sort of the official starting gun for my group to say, okay, you've got permission to go start putting the vehicle together, was in December of 22. And then once the vehicle was built, actually just before the vehicle was built, we had a system level test readiness review, making sure that we had our procedures ready to go, or at least they were on track, ready to go. More importantly, that we had all the facilities lined up that we needed to go to our environmental test facilities. And so where are we at today? The vehicle is 100% built. We finished that officially on June 4th of this year. We've completed all the pre-environmental vehicle testing, so you kind of get a baseline function performance. And then we went into an environmental test campaign. We did vibration testing in July, at the beginning of July. That was interesting. If you remember, we had Burl come through. So we're over in building 13 up on the vibration table. And we were, of course, we had problems, and we were rushing to try and get that testing done. We were able to get that testing done on Friday night. Burl hit, I think on Sunday. We weren't able to get the vehicle out. We left it up on the table, and we actually lost power at the center. So we're in a controlled work area where you got temperature and humidity control, and we lost all that. And we were out of power for about 9 hours and had to monitor everything. Everything was fine, but again, it's sending that one guy in when it's still kind of windy and rainy out. Hey, can you go check on that vehicle? Make sure it's all right. So that was fun. We finished TVAC last month, middle of last month. And that all went great. Right now, what we're doing is we're just beginning the post-environmental test campaign. So we get all the pre-data, how the vehicle was performing then. Now we're doing all the testing of mostly the same tests again, just to make sure everything's working after we went through all that. So that's on the Rover, the vehicle side. There's obviously the mission systems side. The mission control is run out of Ames in their multi-mission operations center out there. So the ops team is primarily out there. So while we've been building the vehicle, they've been working on developing their procedures and then running sims as best they can, and running over and over, trying to get their mission team not just trained, but getting those procedures as mature as they can get it. And they've had hundreds of hours of sims that they've been doing. As an extension of what I would call the core mission ops team, there's also the whole science team. Those folks are looking at the downlinked data off their instruments, and they're changing their ops plans on what they want to go do, where they want to go drill. So as we're roving, the science instruments they're collecting data, they're moving along. There's certain pre-designated sites that they're going to go stop at and do drilling at. But they're also looking at, okay, we just passed a really good spot 3 meters back and on the left. Let's go back over there and go drill over there as well. So they're doing real-time assessments, offline assessments, and feeding that into the mission planning team in order to change their path and their activities to be opportunistic with what we're finding. So that team, the whole science team, getting them trained up on what tools do they need, how do they look at the data, get used to looking at the data, that they've been working on with all that. Lander integration, and I'll talk a little bit more about this, but we were base flying to fly on an Astrobotic Griffin lander. We are no longer doing that. But while we were still working with Astrobotic, we were working on, we have the interface defined, they were working their side of the interface, we had our side of the interface. We had done some preliminary testing, not only of the physical interface, but also driving off ramps. We have ramps, what we were going to use with that lander to drive off, and we were doing that testing with them. And we went through quite a bit of that before our what partnership was ended. And then we started working the range safety packages. Again, the way we were going to get to the moon was we're part of a CLIPS umbrella. CLIPS is the Commercial Lunar Payload Services contract, where they've let multiple contracts out with vendors. There's multiple pre-approved vendors for building landers. Astrobotic was the one that won our task order. That's how we got connected with them to do the Griffin, go on the Griffin lander. When, I guess I'm giving the whole story now. So back in, December, January of this past year, Astrobotic was flying their first lander, which is called the Peregrine lander, and it failed. It didn't even get to the moon. And it was a much smaller vehicle than what the Griffin would be. But in that failure review board, they found some issues with the design of the Peregrine. There was some design commonality with the Griffin vehicle, and the agency lost confidence in Astrobotic having the Griffin lander ready for us to fly when we were supposed to be flying. We were supposed to be flying, well, multiple times. We were going to be flying, well, yeah, we were going to be flying this fall, like right now. Then we were when they had the failure, we reprogrammed to next year, but they're not confident that they're going to be ready for next year either. And I'll talk a little bit more about that. But again, when you contract with these CLIPS folks, they not only provide the lander, but they're also providing the launch services too. So they subcontracted out to SpaceX. We were going to be launched on a Falcon Heavy. And so their negotiations with SpaceX were in work and ongoing. Had already started working on range safety packages. Again, we were supposed to, for one version of our schedule, we were going to be flying right now. So we had already started on that. That really introduces us to, well, where are we at? Right now, NASA Science Mission Directorate has recommended VIPER for termination. There's no lander capable of delivering VIPER within the next year or two. And due to extreme budget pressures at SMD, they recommended not funding any further work on VIPER. And that includes, they didn't want to pay for storage either. So, I mean, if you watch look at my status slide, the vehicle's done and tested. We could fly tomorrow, but they don't want to pay to store it. Now, we're not technically canceled yet because Congress has to agree with that. There is a possibility that they may direct us to direct NASA to continue with the VIPER mission. There is interest in the science community and in at least the House Committee on Science, Space, and Technology of continuing the mission. They sent like 17 hard questions to NASA and SMD to answer, trying to get insight into the rationale for canceling the VIPER mission. And so we're in a state of limbo right now. What NASA is doing right now, a couple of things. One is they've published an RFI request for information to see what industry partners, or at least external organization and partners, might do with the VIPER rover. We've got a vehicle ready to go. Is there someone that would be willing to take the vehicle and get us to the moon and then do something with it? For example, they could collect the science data and sell it back to other people, and they could make some money on the science data or other things. Again, it's a wide open solicitation for getting information. The RFIs were published and the responses are already in. They're currently being evaluated by headquarters, and they're supposed to be done with that evaluation by the 15th. Assuming there's interest, and I believe there is, There may be some industry days coming up where the potential partners would come through and take a look at the vehicle and talk with us, go out to Ames and see what they're doing on not just the mission operations capability, but all the planning that also they've been working on out there. In the meantime, so that process is going on. It's kind of independent from the project at the moment. What we've been told to do is go put together two plans. One is to put a plan together that kind of assumes that something's going to come out of this partnership activity. Tell us what you would do in terms of closing out testing. Again, I mentioned that we want to do this post-environmental testing and get that done. We want to do integrated testing with mission ops guys so we can make sure that their procedures are compatible with the vehicle. Get that testing done. Store the rover. It's going to take a year or two. We need to have a way of storing it. You know, how often do we have to power it up to make sure, you know, all the grease is flowed in the right places and keep the batteries topped off and things like that. And then support wherever this external partnership may go. We're going to have to answer questions. We're going to have to work interface definitions and that kind of stuff. That's one plan. And then there's another plan, which is disassemble the rover and store all the components, keep them in a flight ready condition. That was turned in a couple of weeks ago, and we'll see what happens.
Well, where is it being stored right now?
Right now, it's over in Building 9 South. If folks are familiar with that facility, if you remember the old composite layup lab that was in there, that has been refurbished to be our controlled work area. We turned that into an ISO-8 clean room. And so it's in there and we're doing testing in there right now.
So Ames didn't have storage responsibility.
No, we built it, we get the storage.
And pay for it. Pay for
Well, you know, we get our money from the project office, so it's money flowing from headquarters to Ames to us. So, you know, they're paying for it. In order to get us through this year, there is money. You know, it wasn't like they cut us off totally. There's quite a few $1 million this year for us to get us through this time of limbo. One of the key words in here that I have in italics is gracefully. Gracefully, I don't know if they're, is National Alumni League just civil servants or is it contractors?
It's both.
It is both, yeah. So again, one of the things that's really, really important to the Senate director and the engineering director is it's not just keeping the civil servants employed, but it's keeping our contractor workforce employed. We are more than ever dependent on our community for the technical depth that we have. And so graceful means we need to have an opportunity to place all of our workers into a viable job. So that takes time. That takes time. So Vanessa has fought very hard in terms of getting a good definition of what graceful means.
Is there any info on what the RFIs are like?
I don't. I'm not privy to them. It's sort of a competition sensitive kind of stuff. I'll say, as you might imagine, when there's a wide variation in the technical maturity and realism in some of those proposals. Some of them are not much more than a cartoon. So I'm not going to dwell on the bad news. So that's the bad news. You know, we're working through it. You know, we'll get clarity. It'll evolve over time. We'll see if something happens with these other organizations. In the meantime, you know, we're pressing ahead with testing. You know, it's like I need something very tangible to go do. I'm an integration and test guy. I build things, I test things. So we're going to test things. That's what we're going to go do. And so we're going to continue on. Just kind of going through his picture of the vehicle. This is inside of our clean room area in Building 9 South. Just kind of repeating the dates on what we've completed. Really the best thing, and maybe this is the best news of of the whole project is we don't have any significant discrepancies. You know, what does significant mean? You know, most of the issues that I'm dealing with right now is some bad instrumentation. You know, the thermocouples that are on the vehicle, some of them aren't working. But in terms of primarily functionality, everything is working. NASA, JSC, Engineering Directorate knows how to build spacecrafts still. You know, it's a legacy to y'all in terms of the training that has passed down. There's still people here at this center that know how to build integrated spacecraft. It's getting harder. The talent is getting thinner. We're way more dependent on our contractor workforce than ever before. Our infrastructure is getting old, as you might imagine, but we can still do it. We can still do it. We got really, really good people. The younger people are fantastic. I love working with our 20-year-olds and our 30-year-olds. They're really, really good. They just need the experience. Having the ability to build things is, I mean, you guys know this, is really, really important. Building integrated vehicles is pretty rare at JSC. I've been pretty lucky to be able to do two in a row with AA2 and then this. But it's hard. It's really, really hard. Nothing works the first time you put it together. I mean, nothing. And so there are techniques that you use and you make it work. And our TVAC test was almost perfect. It's pretty amazing. Yes, sir.
I'm a little confused. Does the Artemis, what is Artemis program proceeding because they're confident there is actually water to use? It would seem like something like the VIPER was on the critical path. You don't build Artemis if you don't know for sure that there's water. So
Artemis project is not built on knowing that there's water on the road.
it's not.
Can we hold the questions until the end, please? Yeah, let him finish the presentation, sorry.
I talked about the ground systems dome. This is a picture into their MMOC out at Ames. Again, a lot of time and effort has been put into not just training the team, but getting all the tools in place, including all the mission planning stuff. Oh, well, that's interesting. This is our test campaign. Again, I'm almost all the way through the test campaign. Getting through TVAC was a big deal. That was the last environmental test, and we came through in flying colors. If I skip the rest of that testing, I'd be comfortable going. But we got time, so we're going to go do it. Just some picture in this. Again, this is building 13. It's been in the structures test lab. There's a clean room, controlled work area over there. We were inside of that where we did the vibration testing. We did acoustic testing. So we did this over building 32 in the chamber A clean room area. So, you know, when James Webb came in, they added that big clean room area, which is huge. We used that area to do this direct field acoustic testing. So we had a company called Acoustic Research Systems come in and bring in these 6 stacks of 14-foot tall speakers, and we hit the vehicle with noise and got through the testing. It was a lot. It was fantastic. Actually, it was pretty neat. As you can imagine, you got to get through the safety hurdle there. How do you know you're not going to have the building collapse around you? You know, we got through that. We did some advanced acoustics modeling of the facility to, you know, kind of quote unquote prove that we weren't going to damage anything. And they came in and we got this done in about 4 days from the time they arrived, cleaned off all the equipment. We stacked the equipment with the cranes. Those stacks are, can I remember? 6,000 pounds each of those stacks. And so each stack is composed of like 4 individual speaker stacks. It's pretty amazing. It was a really awesome test to go do. My biggest regret on the project, the guy I was working with, he had an adapter to plug my guitar in. You talked about my guitar. Plug my guitar in, I was ready.
Boomba.
They had a failure in some of their power or their amplifier equipment, and they had to tear the stuff he brought in order to plug the guitar, and they had to tear apart and use. So I never got to put my guitar in. I am going to go out to their facility. I'm going to get that done. I'm going to get that done. Thermal vacuum testing, again, 3 cycles of that. We were able to get all of our objectives completed. We actually got done ahead of schedule. You might ask, how did you get ahead of schedule? Our predictions on our ramp rates were more conservative than what we really hit. So we were able to cool off and heat up quicker than we had going in predicted. And so we were able to get done a little bit earlier. One of the most interesting tests that we did was this hibernation test, 80 hours in a very low power mode. Low power meaning the computer was off and there was a timer embedded into one of the FPGA boards. And so before you fully go to sleep, we set the timer and there's no comm. We had no telemetry. We had test instrumentation to kind of monitor temperatures just to make sure nothing got too cold. And it all worked. I mean, it came out of hibernation, booted itself up. One of the things that we were testing was, okay, how low can we go on the battery stated charge? Because there's still a little bit of power being used. How low can we go on that power and still boot up? Because the minute you start to boot up, all the heaters start to come on to warm everything up. And we needed to make sure that we didn't brown out or get into some kind of reboot cycle where it keeps shutting its load shed, everything's turning off, and you just kind of get into this infinite loop or any other error that might occur. So it was a nail biter only because you have pretty much zero insight into the machine, and it came out great. It was awesome. Maybe that's the other thing too is you can't simulate the thermal environment. So all the testing that we were doing up until then, we're not really testing the thermal control system. We're not really, I mean, yeah, we can turn on and off the heaters, but you're just not working it like it's going to be in the integrated environment. So it was a big learning curve, which reminds me of 2 other interesting facts. One is the vehicle thermal system is designed to work on the moon. When they set it up, the designers didn't think about, well, how are you going to test it? It's going to overheat because we're not most of our testing is not in the thermal chamber. So we actually had to go design, there's not a good way to keep it cool. So we had to watch it really, really close and turn things off. But we also designed a structure that held some fans that would sit right on top of the radiators, not touching, and it would pull air across those radiators. Best of our calculations, it reduced our temperatures by about 10 degrees. Again, but early on, years before we actually ever had anything built, we're worried about the last thing I need is to have to be shutting down the vehicle on every single test and then wait hours for everything to cool off and then try to power up again to go do the testing. And so we did everything we could to try and mitigate that, and that all worked out. The other thing that you can't do is it can't drive on Earth. The wheels will deform and be damaged, so you can't drive. So closed loops testing of the sensor system, like closing the loop around the motors for driving, I can't really do on the vehicle. We didn't build the EGSC to be able to do that. So the way we do that is to test out all the mobility we had. We built some other mobile platforms that were weight appropriate. So again, it's got to be at 1/6 the weight. You offload as much as you can and just keep the minimal equipment set on there to be able to drive, and you can do the mobility studies. One of the things that we're just getting into now is, again, we had to do that early, and as I mentioned earlier, hard time getting hardware. Imagine trying to get test bed hardware, it's even harder. We did a lot of the mobility testing, but with non-flight like, I mean, not even close to flight like hardware. We're just getting now where we have the hardware in our test bed such that we can start driving the motor controllers and the motors with the actual avionics and start taking a look at the power draws. Driving and running that drill are the two big power usage, and you can't quite do that all on the vehicle because you just don't get the loads on it. So that's what we're going to be doing in the test bed. We got some load racks. We got a brake that you put on the drill in order to add some resistance on turning the drill. So it's all very interesting. Actually, maybe another thing that might be of interest. Again, we all grew up doing human spacecraft and kind of have a certain way of doing things. With this robotic stuff, you know, we did try to see where we could take risk and not put in, you know, too much of the extra rigor that's needed. You want to do things that are smart. You want to make sure things work because everything needs to work. But maybe you don't have as many of the you don't have any of the human safety stuff other than ground human safety. So we tried to take advantage of that as much as we could. And that became a real interesting give and take, as it always is on a project. And it was interesting to interact with the Ames research folks who are always dealing with robotic spacecraft, and us always dealing with human spacecraft, and trying to get to a nice compromise between the two. That was interesting. The other item that goes with that is this vehicle compared to our human spacecraft is dumb. I mean, it is really a dumb vehicle. There is hardly any fitter or fault management on board. There's not much of anything. There are limit checkers for temperature, so it'll automatically turn things off when it hits a trigger point. There's some triggers for power management, so at certain times if the power loads get too high, it'll do awesome automatic load shedding, and that's about it. Everything else, well, and the only other thing that it's got is if it gets a loss of comm, and this is the smartest thing on the vehicle. So as I mentioned, the way we do driving is the driver's kind of pointed in a direction and you just let it go for X number of meters. If for some reason it gets to the other end and it can't reestablish comm, it'll go through, you know, the antenna search patterns and all that kind of stuff. It will also retrace its steps back to the last spot it had good comm. That's the smartest thing that's on board. Other than that, it is highly ground monitored and for the vehicle. There's hardly anything on board. This is one of the glamour shots of the vehicle going into the chamber. The only other thing that's missing on this photo, but again, we needed the glamour shot of the vehicle. There's a radiant heat enclosure that goes over the top of this thing. So you take the chamber down in temperature, and we were down at like 14K on the helium shrouds. But you still need to heat the vehicle up. So you've got heat coming off the ground. So there's panels underneath. You got the sun hitting one side or another side. And so the enclosure panels had heater bars in it, and we were using those to heat up the vehicle. So when we got into the hot thermal balance portion of the test, we needed to have have that heat enclosure to be, operational, again, a whole nother design effort. A little bit about science. Again, the team out at Ames has been working with the science community. Again, 60 people from across multiple agencies to be a part of that team. They've got different, they call them hypotheses, but ways of potentially determining water and water concentrations based on the measurements that they're getting. And they use that information to, again, decide how they want to go search for these water volatiles as they're exploring the South Pole. Obviously, there's displays for allowing them to do that work. Path planning takes a very long time. Everything's pre-planned. They have opportunities for opportunistic, but it's limited. Again, we are trying to outrun the shadows. We're always need direct field of view of the earth for calm. So you're kind of always on the move. The way they like to think about it is our safest condition is while we're roving, because we're outpacing the shadows. I talked a little bit about the rover interface to the lander. We have a rover release mechanism with both sides of the actual separation plane. We own that separation plane and put that the lander side of the interface is what it's just a bolt pattern that the lander folks need to correspond with. And then there's the data and power connections. We can get power from the lander. We can get data from the lander. We can talk to our vehicle through the lander. And so working through those disconnects was another test that we did in TVAC, that rover release mechanism. Again, if you can't get the rover release mechanism to work, your mission is over because you're not getting out that lander. We had done quite a bit of planning of what we were going to do out in the payload processing facility. Again, we had it scoped out for what we do post ship while we still own the vehicle. Then we hand the vehicle over to, in that case, it would have been Astrobotic. We work with them to get us mated to the lander, and then we do integrated testing, make sure that we can power up the vehicle off their power, make sure that we can talk to the vehicle, make sure that we can talk all the way back through their control center, all the way back out to the Ames control center. All that stuff was in various states of completeness. And then I kind of mentioned the launch safety packages. We've already been through the safety review #1, had our approvals for that for continuing on. Our TSC stuff that we're going to be taking out there was all approved. So we were making good progress there as well. Again, we've got a vehicle that's ready to go. We're just sort of waiting for further direction. We're charging ahead. We're assuming that we're going to get to fly. I did have like a few minutes with Vanessa yesterday, and she noticed I was wearing my VIPER shirt, a different VIPER shirt yesterday, and she said, "We're going to get you to the moon." I said, "Thank you." Well, so we'll see what happens. And with that, I'll open up for questions.
All right.
Sorry about that. If I took too long, I don't know.
No, you're fine. You're fine, actually. So do we have any questions in the room? First of all, we'll take a couple questions from the room, and then if you could mind the chat. For those of you online, if you could put your questions into chat, and we'll check the chat and read them out in the room, okay? Okay, so we have a question over here.
Yes, sir.
What has the VIPER cost so far?
Our
We talked about.
we're a little less than 500 million for our part of the vehicle. So we're sitting at like 475 million for the vehicle. The amount we contracted for on that lander was like 250 million. That money's spent and gone.
So two questions. How many people are on it that might lose their jobs? And the second, are you gonna have to go through the lunar nights and survive them?
On the people side, at our peak, and I can only really talk to my numbers. My system integration and test org combined with the Rover design organization, again, they ramped down because most of the design was done. So we combined the organizations. At my peak, I was about 350 people. We're down at about 150 right now. And we're ramping down pretty quick. Now that we just got past TVAC, there was 100 people involved in TVAC alone, trying to 18 days around the clock was a lot. For lunar night, yes, we do go into that hibernation mode when we don't have calm and we don't have sunlight. So we go into that very, very low power mode, and we can survive up to like 50 hours in that mode. So we don't go through a full lunar night because they're doing the path planning and they're going to take us to a safe haven spot that says, park here. This is the shortest amount of time that we will be in the night. We'll wait for the shadows to pass by and the sun will come back and the earth will come back and we'll be good.
So that's batteries? It's on batteries during that thing?
Yeah, at a very, very, very low state of discharge, yeah.
Was there any consideration to RTGs?
That decision was made before my time, and what I was told was that they didn't want to go fight the bureaucracy to go make that happen.
6 of them.
Oh, I'm sorry. Yes, I'll repeat the question.
6 of them on the moon.
So the question was, did we ever consider using RTGs or any of the radioactive materials, like just for heaters would have been nice too. Because they got wiring, I could say. It was yes, but no, they didn't want to go fight the bureaucracy to go make that happen. Yes, ma'am.
I have a question about the cameras. When you said that you're taking pictures to know which path you're going on, do you guys also take into account for maybe what if the lenses get dirty? Like, was there like some type of carbon windshield wiper or some way of handling that?
There's no cleaning of the lenses. So the assumption is that if they get dirty, they're not going to be dirty enough to impede any of our operations.
And then I have a second question. When you were doing testing, did you also test for different types of lighting in case there's like older stuff and did it handle decently well?
Yeah, so the question was, did we test for different lighting conditions? There's actually been an extensive amount of lighting testing done, not so much with the vehicle, but out at not with the flight vehicle, but with the mobility platforms that I was talking about. They have a lighting lab out at Ames, so they put it in that lighting lab, and they can mimic the lunar conditions with the sun and the various shades of gray. And they've done quite a bit of testing out there and what the drivers see and can see, and just a lot of testing with that. And that goes back before VIPER was started. It's been going on for quite a while. Yes, sir.
Yeah, so back, maybe I think it was slide 19, a couple of slides back, you had something I think on a lunar gravity. Yeah. Wondering if you could explain a bit more. Yeah, there it was. Movement, gravitational representative unit.
Yes.
A little bit more into what you did about the 16G and what.
Yeah, it's basically offloading everything. So take off, there's no batteries, there's no power system. All there is the flight computer, and it's not even the full flight computer, and the motor drives actually drive the wheels. So you can get rid of just about everything off it. Now they've augmented it for different kinds of testing, like when they wanted to use the platform for doing like tracking the sun. They added some structure to hold like where the antenna was and be able to point at the sun. It became less about the dynamics and more about can I do the tracking. So they didn't always keep to the 16G depending on what they were trying to test.
So, but like the drive wheels and that sort of thing is done with just a lighter.
Exactly.
Lighter
Everything's
configuration. configuration of
Right.
the same unit.
Think of a guy following along with the vehicle with an umbilical and a little hand controller set, driving it.
Not having counterweight, offloading of.
Mhm, mhm. Other questions? Yes, ma'am.
One last question.
No, you're good.
What about the soil composition? When I've been told that sometimes we're not certain that the soil may be firm enough, it may be too loose. Was that taking consideration in the development of the, I want to say wheels, but
No, it's primarily the wheels and some of the mobility modes that it can get. So the question was the soil mechanics, the regulative dynamics taken into account into the design of the vehicle and the design of the wheels? Definitely, yes, probably the thing that's been most studied over the years, and I may be stretching a little bit, but what is the proper wheel design? There's a lot of different wheels designs. You'll notice on this vehicle that, you know, the wheels are relatively small in diameter. They got fins on them, fins for lack of a better term. They're spoked. And again, I do not know all the details of why they picked that wheel design and the rationale on it, but I know it precedes VIPER, and it may even precede Resource Prospector. A lot of went into it. Now, they do testing in the rock yard here at JSC. That's sort of, in my mind, it's kind of a low fidelity test bed. The higher fidelity test bed for that is up at Glen. And so we took that reduced gravity mobility platform up to Glen several times, and they worked in that box. And that box can be inclined. You can put other, it's lunar simulant in that test bed. And then you put rocks in there as well. And I talked about modes. There's a mode, which they call a swim mode, where you can use the wheels like in a flipper motion, where they're kind of pushing through. If it's really loose, fine grain, regular powder, you swim through it, and they demonstrated that mode as well. And you actually swim through that really fine powder. So that they've addressed it multiple different ways. Go ahead.
what if the VIPER, like, for some reason they miss something in the image and it flips over? Was there any like lever that pushes it up to be a vertical, upright, or anything like no?
No, if it loses dynamics, if it loses stability and tips over, we're done.
Any other questions from the room? I don't think we're not seeing anything on
Nothing on
chat.
chat.
Okay, so again,
I do one more.
hang on a second. Yeah, I just want to make sure that the folks online, if you have any questions, if you'll put them into chat. David's monitoring the chat, and then he has another question.
So are you also doing the analysis and other methods for verification? Or you just work?
Now with my combined organization, yes, with the Rover folks and the folks who actually own the Rover requirements, they're going through their verification closures right now.
So what are you doing between the analysis and the test counts? Your split of what you're doing.
You mean like percentage wise?
So just kinds of things that you're doing with analysis versus test. Dust maybe, is that an analysis?
You know, I can't speak to dust a lot other than dust has not been a driver requirement for this vehicle. Early on in the startup of VIPER, the designer for dust mitigation, which is primarily in the mechanisms in the motors, they came up with a way in which we basically put on socks on the vehicle. They double as contamination barriers, but also MLI insulation. And we keep basically the way on contamination, we just keep the dust out. Dust is not a problem. We live with any kind of dust that may accumulate on the solar panels, but the solar panels are on the side. So other than kind of static cling, for lack of a better term, we don't have it. Radiators may be a little bit more problem because they're sort of flat. You might get radiator, degradation with an accumulation of dust, but it's not been a big driver.
You have fluid in your system.
We have fluids in there. It's a propylene,
So how
fluid.
about 1,6G on the fluid?
We had to do testing on that, so it's easier to get it to work in 0G to get those fluids moving. So when we did our TVAC in 1G, sitting up like how we are, it's sort of in some regards, it's a worst case situation. We were able to force on the fluid loops to get them to go in the right direction because they can reverse flow. So we got really good operationally being able to recognize the conditions, get things to flow by turning on the heaters and getting things to flow. We also did a couple different TVAC tests with one radiator and one loop heat pipe where you put it on its side and you get it's not fighting, the fluid's not fighting gravity as it's angled. So they kind of set the angle, and I can't quite remember the degrees, and they kind of worked it that way on that. I'd say for the analysis, the biggest thing that we've got going with analysis is the thermal modeling. The vehicle is driven, the driver requirement is the thermal system and the extremes that the thermal system has to deal with. It will overheat and it will freeze. And so if you look at the vehicle, it is not just the thermal management system with the loop heat pipes, but it's also layers and layers and layers of multi-layer insulation. Anything, the way the vehicle is constructed, there's a warm box on the inside. Most of the avionics is in that warm box, and on those we call them heat spreaders, there's pipes going through it, and that connects to the radiators. That stuff's fine, but all that gets wrapped in MLI multiple times. Anything outside that warm box is also wrapped in MLI. All the harnesses that reside on, all the harnesses going out to the motor controllers out at the wheels, they're all wrapped in MLI. Everything you see on the vehicle, and this other than the solar panel, that's all multi-layer insulation. Everything's covered in it. We had I can't say this is true. That's just what I was told, but there's more multi-layer insulation on this thing than there is on the James Webb Space Telescope. It's hard to believe because this is way smaller, but that's what I was told, so I'll pass it on. But doing the thermal modeling, getting the models correlated to the TVAC test is a big deal. It takes months and months and months to do that, and it's going to be really hard. Power has been the other modeling part to support the analysis, because ultimately you got to translate all this test data into what would you call it? Either operational constraints, or maybe we could come up with operational envelopes. Getting that understanding is challenging and hard. So that's, in my mind, one of the biggest challenges for analysis. Side comment, one of the things that we didn't do when setting up the project was we did not do a good job of setting up design analysis cycles. And so you had some independent, it wasn't complete analysis, and the analyses that were done independendly. So you get the power guys doing their analysis and the thermal guys doing their analysis, and they may meet every once in a while and try and sync it up, but it wasn't rigorous enough, and it came back to stress us, right? Because as you're going to the TVAC and you realize, well, you did all these analyses for the moon, but you know what? I got to get through TVAC. I need predictions for TVAC. What are we going to do? What temperatures are we going to? It took a lot of effort to get things turned around, to be able to be complete and to get them synced. Because when you're getting cold and you're turning on heaters, you're draining the batteries. And it took a while to figure out, to make sure that we weren't going to drain those batteries.
What redundancy does it have?
There's no fitter, there's really no redundancy on. I'm trying to think of something that's redundant. And there's not, There's nothing, I think there's something redundant on, but I can't think of it at the moment, so it's not obvious. There's not a lot. Now, that doesn't necessarily, I mean, that's different than are there single point failures? I mean, yes, we have those too, but we can complete much of the mission. So for example, here's probably the best redundancy that we have. The capabilities of our instrument complement are overlapping. We can still achieve full mission success if you lose one of the instruments. So there's, that would be a dissimilar kind of redundancy thing in order to meet all your mission objectives. So there's some clever things like that were done, at least with the science. Power's got 2 batteries. That's probably, yeah.
I'm sorry, you might have mentioned it, but what about the lander? Who built it? Is that built and the rep and everything?
No, we don't. We do not have the vehicles. This vehicle's built, but the lander is not built. There is nobody who has a lander that can take us from. The company that we had contracted with is that relationship has been severed, and we are not going on that lander. So Astrobotic, who was going to build the Griffin lander for us, VIPER is not going on that lander. But there's no one else who has anything big enough yet. We're probably a year or 2 away.
So I have a question
Yes,
about
ma'am.
the science. On one of the slides, I think you showed a finite number of hypotheses.
Oh,
that
yeah,
the
yeah, yeah.
Science community had, or still have. Does that indicate a specific life expectancy for this vehicle, or is there the life expectancy, kind of like what we saw on the Mars rovers, where they were only supposed to last X number of months, but with appropriate operational management, they can last a lot longer and could potentially do a lot more science than what is currently hypothesized.
I have a different interpretation of this, which is
Perfect.
there are multiple hypotheses that you can use that can indicate water volatiles or concentration of water volatiles. Each hypothesis leads to a different result. And what they've done is they're synthesizing between those 37 to construct the best mission profile that they can. So here's a simplistic way of thinking, and I'm not sure it's correct, but this is my way of thinking. It's like the hurricane models. You got the different paths that the different models say to go, and you look at, okay, it makes sense that it's probably going to go in this direction because 5 out of the 6 models is going to go to. That's how I kind of view this. Most of the models say we should go on this path. Well, let's go that route. But maybe on a different part of the mission, we want to test other hypotheses because maybe they're better, even though it's not part of the consensus, but it might be the best one there is. So that's how I view it, but I don't know anything more than that.
So does that kind of indicate a life expectancy for VIPER itself once it's on the surface?
No, the life expectancy is going to be, it factored more into just the lifetime of the equipment. And to be honest, I have a hard time identifying what's going to break first. So I think there's a good, like with many NASA spacecraft, we're going to far exceed the 100 days unless there's something in our infant mortality rate, or we just totally miss something, But I mean, the batteries are going to be good for 8 to 10 years. Maybe the motors wear out. Something comes loose, we lose connections because there's not redundant connections on things. I could picture that happening.
What grade of electronics is in this? Is it commercial, industrial, military?
It's I guess I would care. It's screen commercial parts, but it's mostly commercial parts. Screen commercial parts.
Did you radiation screen them or just?
Some were, and some we have gone back and done some testing on, and we actually have some testing coming up in December where we're gonna go look at some susceptible parts. We did not go the high grade, I forget what you called it, but the high grade parts, we
Yeah,
didn't go
those
that
quick.
route.
Radiation hardened.
Too hard to get and too expensive.
Your questions? Now or?
All right, well, thank you very much.
Staff is sick. These days.
All right, David, thank you very much, and thank you to everybody in the room. Thank you to everybody who joined us online. That is going to conclude our presentation and ergo our meeting for today. Our next NASA Alumni Association meeting will be on Thursday, Thursday, November 7th. So at that point, I think we'll know, election results and probably be really close to knowing who will win the World Series. You can pick whichever one is more important to you. So again, the meeting has been recorded, and that recording should be available to you within a couple of days on the NAL website. So thank you very much.
I had a question of Dave.
Yeah.
How come